Alright folks, we are back. In this video we are going to talk about information from section 7.7 of AP Calculus, finding particular solutions using initial conditions and separation of variables. Alright, so really all we're doing in this lesson is we're combining a couple of things that we've done before. We're going to go ahead and find the general solutions using separation of variables like we did in the last lesson. And then we're going to add one more step to that. We're going to substitute in the initial condition, solve for the value of c, and we will get one particular specific solution that meets both of the characteristics. Its derivative is the differential equation, and it meets the initial condition as well. So let's go ahead and we're just going to look at a bunch of examples here. Example 1, part A. Find y if dy dx equals x squared y and y equals 5 when x equals 0. So when this says find y, it means we're finding the function for y. So we're going to start by separating dy dx equals x squared y. We'll divide both sides by y, multiply both sides by dx, and that gives us dy over y equals x squared dx. And now I'm going to go ahead and integrate both sides. And this is a natural log of the absolute value of y, and this is going to be 1/3 x cubed plus c. And now in order to solve for y, just like we did in the last lesson, we're going to raise both sides e to that power. Turns into absolute value of y equals c e to the 1/3 x cubed. I can absorb the sign into the constant, and so this is equal to y equals c e to the 1/3 x cubed. And now I'm going to go ahead and use my initial condition to solve for the constant. So it says here that y equals 5 when x equals 0, so I'm going to put 5 into this equation for y, and I'm going to put 0 in for x. And so we have e to the 0 power, which is just 1, and that tells us that our constant of integration is 5. And therefore, I'm now going to put that constant back into the general form. So y equals, and I'm going to replace the c with a 5. And this is the one particular form of this equation that has its derivative, dy dx, and also meets the characteristic that y equals 5 when x equals 0. Alright, let's do another one. Find y if dy dx equals y over x and y equals -2 when x equals 1. Okay, so let's go ahead and separate. I'm going to divide both sides by y and multiply both sides by dx. And we get dy over y equals dx over x. I take the integral of both sides, gives me the natural log of the absolute value of y is equal to the natural log of the absolute value of x plus c. I raise both sides of this equation, e to that power gives me absolute value of y equals c e to the natural log of the absolute value of x, which now that's just going to be the absolute value of x. From this absolute value, I can absorb the constant, the sign into the constant. I can't do that with the other side, though. And so we get as our general solution y equals c times the absolute value of x. And now we're going to go ahead and use the initial condition in order to determine the value of c. So y equals -2 when x equals 1. So we get that c is equal to -2, and our specific solution is going to be y equals -2 absolute value of x. Excuse me. All right. Now for a couple of not old, but a couple of AP free response questions that involve separation of variables. Let's look at example 2. This comes from the 2021 AP Calc AB exam, free response question number 6. We have a medication that is administered to a patient. The amount in milligrams of the medication in the patient at time t hours is modeled by a function y equals a of t that satisfies the differential equation dy dt equals 12 minus y over 3. At time t equals 0 hours, there are 0 milligrams of the medication in the patient. So that's our initial condition there. Part C of this question was to use separation of variables to find y equals a of t, the particular solution to the differential equation dy dt equals that with the initial condition. All right, so we're going to go ahead and separate first. We divide both sides by the quantity 12 minus y, and we multiply both sides by dt, and we get that. And now we're going to go ahead and integrate both sides. The integral of the left is negative natural log of the absolute value of 12 minus y. And the integral of the right is 1/3 t plus a constant. If you're unsure why this is a negative, do this using substitution. Substitute u equals 12 minus y and see what happens when you take your du. All right, so now I'm going to multiply both sides by the negative to get rid of that negative sign. And now I take both sides of the equation, e to that side, and that turns this into the absolute value of 12 minus y is equal to c e to the negative 1/3 t. Then I'm going to go ahead and absorb my absolute value into my constant. And continue solving for y. I'm going to subtract 12 from both sides. And multiply both sides by -1. And now I think I'm just going to go ahead and find my initial condition. I've already got the equation in terms of y. Now I could have at any point in time put my initial condition in here and solved for c. But then what happens is you actually have to do the calculations with that constant. It doesn't stay the same the whole time. It's not like we can do the constant magic where we just change constant into other constant. We actually have to keep track of the algebraic steps if we do it that way. So in general, I tend to prefer getting my y and isolating it if I can before I solve for my initial condition. That's a personal preference. I think a lot of people you'll find, do things that way. So we'll put the initial condition in now. 0 is equal to ce to the 0 plus 12. And so 0 is equal to c plus 12. So c is equal to -12. And so y is equal to -12 e to the negative 1/3 t plus 12. And there's your particular solution to that differential equation with initial condition a of 0 equals 0. All right, one more example. Example 3 comes to us from the 2019 AP Calculus A/B exam from free response question number 4. A cylindrical barrel with a diameter of 2 feet contains collected rainwater as shown in the figure to the right. The water drains out through a valve not shown at the bottom of the barrel. The rate of change of the height of the water in the barrel with respect to time t is modeled by dH dt equals -1/10 square root of h, where h is measured in feet and t is measured in seconds. At time t equals 0 seconds, the height of the water is 5 feet. Use separation of variables to find an expression for h in terms of t. So we're going to start with our differential equation, and we're going to use separation on this differential equation to get us to find an equation for h. So I'm going to divide both sides by the square root of h and multiply both sides by dt. My separation is done. I'm going to go ahead and integrate. The integral of dh over the square root of h is 2 square roots of h. Again, you can use substitution to do that. I just do mental substitution. I've done so many of these over the years that it's almost a no-brainer. And then we integrate the right-hand side as well. And now we need to start solving for h. I multiply both sides by 2, or pardon me, by 1/2. And then I square both sides. Now I can solve for my initial condition. I substitute 5 in for h when t is 0, so we end up with 5 is equal to the quantity negative 1/20th times 0 plus c, quantity squared. So 5 is equal to c squared. So c is the square root of 5. And therefore, I go back and I substitute that c back in here. And you've got to make sure, here's the thing, another thing to think about. Got to make sure you substitute your c back into whatever form of the equation you used to solve for your c. This was the form of the equation I used, so it's appropriate for me to bring my c back into this form. It would not be appropriate for me to bring my c in back here, because that's not the setup that I used to solve for that c. This is going to be a different constant. If I had put the initial condition in there and solved for c, I would have gotten a different constant. Alright, so now we're putting this back in, negative 1/20th t plus the square root of 5, quantity squared. And there is my solution, my expression for h in terms of t. Alright, and so that's how we find particular solutions using the initial conditions and separation of variables. Go ahead and do some practice with that, and we'll see how things go from there. Alright. That's it for this video and for this section. We'll come back next time for section 7.8 of AP Calculus, which is on exponential modeling. And so we'll be back for that one next time. Exponential models with differential equations. All right. Have a great rest of your day, everybody. See you when I see you again. All right. Bye-bye.